name of God. Hello everyone. I'm so glad to have another session with you, and I really again hope that you can take good lessons from this video. In last video, we discussed about different nanostructures, their properties and applications. In this video, we want to see that how we can relate carbon atoms to the nanostructures and last topics. We all know that carbon atoms has a lot of secrets behind them. They have many applications and properties that makes millions of use of them in industries and technology. So let's start with carbon's properties. We know that atomic number is 6 and atomic mass is 12. And it has many forms. That 5 main forms are graphite, that we see that in pencil lead. It's graphene, that is one layer of graphite, and it goes on the paper when we write with our pencil. We know that diamond is one structure or form of carbon that is not just so beautiful and bright, but it also is one of the hardest materials found on Earth. We have fullerene that we're going to discuss about later, and we have carbon nanotubes that we have discussed about them a bit in one-dimensional nanostructures. Let's start with graphite. Graphite is a hexagonal structure with carbon atoms that are formed together and bonded together with sp2 bonds, and it's made up of layered sheet of graphene spaced 3.354 angstroms apart, and there are strong covalent bonds between the atoms in the graphene sheet, which you can see here. This is the graphene sheet, and when we just form these graphene sheets in a layers with 3.354 angstroms apart, we can form graphite, and we are going to know the properties later again. And we have van der Waals forces, weak van der Waals forces between the graphene layers in the graphite structure. And these van der Waals forces are holding together the graphene layers in the graphite structure. And in each layer, the carbon atoms are arranged next to each other in a hexagonal shape, which you can see here. So let's talk a bit about graphene to know more about graphite structure. Graphene is a layer of graphite. When you write, as I said, when you write with your pencil, it's a layer of graphene which is going on the paper. And as you can see, carbon atoms are covalently just bonded to a carbon atom next to them, and the distance or the length of these bonds are 0.142 nanometers, and the bond angles, as you can see here, are 120 degrees. So when we form them together, we have a sheet of graphene. And well, if we roll a single structure of graphene, around an axis, it's formed a one-dimensional nanostructure, which we called nanotubes in the last session. So as you can see, it's a nanotube that is a sheet of graphene rolled around an axis. And if we, twist it in a spherical shape, it forms a fullerene or a buckyball that has many structures. As you can see here, we have hexagonal and pentagonal rings in the fullerene structure, and is also a graphene sheet which is twisted into a spherical shape. So knowing more about graphene, well, we have one layer, bilayer, or few layers of graphene holding together. For example, we call one layer of graphene, and 3 to 10 layers of graphene is called few layer graphene. 10 to 30 layers of graphene is called, thick graphene, and over 30 layers of graphene is called graphite. Well, here we are going to discuss about diamond. Diamond is a very hard structure, and it has a cubic crystal structure, which in that carbon atoms are arranged in a tetrahedral configuration with sp3 hybrid bonds. And the strong covalent bonds has made diamond one of the hardest materials known on Earth. And one of the important uses of diamonds is not only in jewelry, but it is used for grinding and polishing metals and coating for cutting tools. And other structure that we're going to talk about is fullerene, which is also named buckyball. It's a spherical structure consisting of rings of hexagonal atoms forming together and rings of pentagonal atoms, carbon atoms coming together. And one of the most famous fullerenes we know is C60. It's made up of 60 carbon atoms in 20 hexagonal rings and 12 pentagonal rings. And one of the most important applications of fullerenes is drug delivery. It can deliver our drugs to the right cells that we want the drugs to deliver to them. And it can have more or less, carbon atoms than 60. For example, here we see a smaller fullerene that has fewer carbon atoms than 60 carbon atoms. For example, we can have fullerenes with 20, 24, 28, or for example, 36 carbon atoms. And we can use different atoms in our fullerene. For example, carbons can form fullerenes alongside with nitrogen atoms in our fullerene buckyballs or structures. And first, for explaining the next form of carbon, which is nanotubes, we can have a review on one-dimensional carbon structure and one-dimensional nanostructures. Well, carbon nanotubes are one-dimensional nanostructures which have the diameter and the surface of less than 100 nanometers, but length of more than 100 nanometers, which you can see example or a shape here. And the length of these nanotubes is normally between 20 nanometers to 5 micrometers, which you can see is more than 100 nanometers or bigger than nano size. And their diameter is between 0.2 to 4 nanometers, which causes the surface about smaller than 100 nanometers or in nano size. And one of the most important things we should know about them is that they can be single or multi-wall nanotubes that have different applications. For example, you can imagine a smaller nanotube with smaller diameter into this nanotube. And if we can have a few of these nanotubes going inside together, we have a multi-wall nanotube or carbon nanotube. And between these multi-wall nanotubes, there is a distance about 0.38 nanometers or more. So at least we have 0.38 nanometers this distance between the carbon nanotubes that we have in multi-wall carbon nanotubes. And about their properties, we can say that they have a great chemical stability. They have unique tensile strength, 100 times greater than steel, and high Young's metal. And they are lighter than aluminum with a surface area of up to 1,500 square meters per gram. This is a very big surface area, and they have thermal stability up to temperatures about 1,000 centigrades. Its thermal conductivity is about 6,000. There are very important properties that we can use in different industries and technology. And at last, let's just say that carbon nanotubes have different conductivity based on the arrangement model of hexagonals and carbon shapes that they are arranged next to each other to form our nanotube. So at last, we can see a video about the different properties to have a review on different properties of nanotubes, of carbon nanotubes, and their use in technology and industries. Let's see the video and then we want to continue our topic.
Carbon nanotubes, a one-dimensional carbon material. They were discovered about 10 years ago. A new molecular form of carbon discovered a whole series of new and unexpected physical, mechanical, and chemical properties. These unique properties make nanotubes a key element in nanotechnology. Carbon nanotubes are cylindrical, elongated structures with a diameter 1 to several tens of nanometers and can be up to several centimeters long. They consist of one or more hexagonal graphite planes rolled in a tube, a hemispherical head at the end. According to a definition, the basic classification of nanotubes is carried out by the method of folding the graphite plane. This folding method is determined by two numbers, n and m, which define the folding direction expansion to the translation vectors of the graphite lattice. This is illustrated in the picture. According to the value of parameters n and m, two types of the following types of nanotubes are distinguished: direct nanotubes, armchair or spike tooth, n equals m; zigzag-like, zigzag, m equals 0 or n equals 0; helical, chiral nanotubes. One of the remarkable properties of carbon nanotubes is that their properties depend on geometry. Their electric properties in particular depend on angle of torque. Carbon nanotubes can have metallic and semiconducting conductivity. Metallic nanotubes conduct electricity at absolute zero temperature, while the conductivity of semiconducting tubes is zero at the absolute zero and increases with increasing temperature. Nanotubes can be used in the following areas: mechanical applications, heavy-duty fibers, composite materials, and nanocycles. Applications in microelectronics, transistors, nanowires, transparent conductive surfaces, and fuel cells, to create connections between biological neurons and electric devices in the latest neurocomputer developments. Capillary applications, capsules for active molecules, metals and gas storage. Optical applications, displays, LEDs, medicine, in active development.
Okay guys, you have seen a video about properties of nanotubes and their applications. Now we have chiral arrows as another topic that are used to classify our different carbon nanotubes. Let's see how. Look at this slide. We can see A1 and A2 arrows at the bottom of the page, and A1 arrow is an arrow that is directly between two carbon atoms, and one carbon atom is the distance between them. And A2 arrows is also like that, but in a different direction. So like the arrows that we use in mathematics, we use these arrows, for example, about the direction that they are going these units in different directions. For example, look at the blue arrow. We have an arrow that is 1, 2, 3, 4, 5, 6, 7 units in the direction of A1 arrow. And we have red arrow at the up of the image, which is 1, 2, 3, 4 units in the direction of A2 arrow. So how we use them? First, let's say that we have N and M in this slide that we use for counting the units of these arrows which we are going forward in different directions. For example, we use N for A1 arrow, so we have got forward, for example, 7 units in the direction of A1, so our N is 7, and 0 units in the blue arrow, 0 units in the direction of A2 arrow, so our M is 0. And we name this 7 and 0 arrow. And in the red arrow, you can see that we have got forward 1, 2, 3, 4 units in the direction of A2 and 0 units in the direction of A1. So we name this arrow 0 and 4. And if you look at the orange arrow that we have at the bottom of the image, we can see that we have got 1, 2, 3, 4, 5 units at the direction of A1 arrow and 1, 2 units at the direction of A2 arrow. So we name our arrow 5 and 2. So how we use this mathematic topic for using and classifying our nanotubes? Well, let's just say if we go in the direction of A1 arrow, like you can see in the blue arrow, and cut our graphene sheet in this direction, our nanotube is called zigzag nanotube. You know, the direction is N and 0. We have a number for N, but no number for M. So the arrow is N and 0, and our nanotube is called zigzag nanotube. If we go at the direction of our red arrow and we have some units for M but 0 units for N, our nanotube is called armature. You know, we have a number for M but 0 numbers for N. And we have cut our sheet, our graphene sheet, in the direction of this arrow and rolled it. Our nanotube, or the synthesized nanotube, is called armature nanotube. And if we cut our graphene sheet in the direction of, for example, orange arrow, which has some units for N and some units for M, and none of them is 0, and we cut our graphene sheet and roll it, the nanotube that is synthesized is called chiral nanotube. So this is a way for, classifying our nanotubes, and naturally, based on which nanotube we have, it has different applications and properties that can be used in, different fields. So this is a way to classify our nanotubes, and naturally, based on the way of synthesis and the categories that we have for them, they have different structure, different applications, and different uses in different fields. So this is the way we classify them, and that was the last topic I wanted to discuss with you. In next sessions, you will know about different tools that we use for characterize the nanostructures, for different ways of synthesize the nanostructures, and I really hope that you could get some answers for your questions from this video, and you could learn good things from this video. And thanks for watching us. Bye for now.